We are usually taught, from a very early age, that a solar system is mostly empty space, that the planets float in a clean vacuum, that the Earth glides through nothingness on its long path around the Sun, losing nothing, gaining nothing, carried along by gravity through a medium so thin it might as well not exist. This is the standard picture. It is the picture we draw in textbooks and project onto classroom walls. A yellow dot in the middle, a blue dot circling around it, a vast, featureless void between them. For most of the universe, that picture is accurate enough. Space is genuinely, profoundly empty. The average density of matter in interstellar space is so low, if you compress the emptiness of a region the size of the Earth into a single cubic centimeter, you would find fewer particles than you can count on one hand. The vacuum of space is a better vacuum than anything we can manufacture in a laboratory. For the purposes of understanding how our own system works, the approximation that space is empty is perfectly serviceable. Earth loses no energy to friction. Its orbit does not decay. It will continue circling the Sun for billions of years without slowing down. But right now, tonight, if you go outside and look south on a clear winter night, you can find a star that is breaking this rule in spectacular fashion. That star sits in the constellation of Orion. It is the bright red point at the hunter's left shoulder from our perspective, or equivalently, his right shoulder from his own. It is one of the largest and most luminous stars visible to the naked eye. And for decades, we thought we understood it. We thought it was a single object, a lonely dying giant, pulsing and swelling on its own, running out of fuel in the vacuum of space. We were wrong. The star is called Betelgeuse. Its formal astronomical designation is Alpha Orionis, meaning it is the brightest star in the constellation of Orion. Its name comes from the Arabic phrase Yad al-Jawza, meaning the hand of the central one, a reference to its position in the figure of the hunter as described by medieval Arab astronomers. Over centuries of translation and mistranslation, this phrase was corrupted into Betelgeuse, a name that has no direct meaning in any language, but has become one of the most famous star names in the world, partly because of a movie, partly because astronomers themselves have used it with such frequency and such urgency that it has lodged itself permanently in the public imagination. Betelgeuse is not just a bright star. It is a red supergiant, and the difference between a supergiant and a regular star is so enormous, it is almost impossible to express in ordinary language. If you replaced our Sun with Betelgeuse and placed it at the center of our solar system, its outer atmosphere would extend the orbit of Jupiter. In some estimates, it would reach all the way to Saturn. The star would engulf Mercury, Venus, Earth, Mars, the asteroid belt, and the largest planet in the solar system, without even noticing. The surface of Betelgeuse as seen from where Earth currently orbits would fill the sky from horizon to horizon. There would be no sky. There would only be star. And yet, as impossible as this scale is to comprehend, it turns out that even Betelgeuse is not alone. Astronomers have now gathered strong observational evidence for the existence of a second star, a companion trapped in an orbit inside the outer atmosphere of the supergiant. This companion is a main-sequence star, probably roughly similar to our own Sun. It orbits the core of Betelgeuse roughly every 200 days, or about 6 years. And it does not orbit in clean vacuum. It orbits inside the outer envelope of a red supergiant, plowing through gas that is thin by the standards of planetary atmospheres but impossibly dense compared to the void of interstellar space. It fights friction with every revolution. It loses energy with every orbit, and it is spiraling, slowly but inevitably, toward its destruction. We call this the safe event, named for the star in Orion's foot, though some researchers refer to the companion itself as Betelgeuse B. In more poetic naming conventions, Siwara, a name drawn from the Arabic word for bracelet, evoking the loop the companion traces around its monstrous host. Whatever name we use, the reality is extraordinary. We are watching, in real time, one of the rarest and most violent events in stellar astronomy. We are watching a common envelope binary system, a star inside a star, playing out in our cosmic backyard, close enough that we can resolve the details in our instruments, close enough to study with telescopes we already have. This is a story about what is hiding inside the light of a single star, It is a story about how ancient human observers tracked a mystery they did not have the physics to solve. It is a story about a false alarm that became a gift, about a cosmic sneeze that distracted the world but also handed us the data we needed to finally crack a century-old puzzle. And it is a story about what happens when the rules we take for granted about empty space turn out to have a spectacular exception, sitting 700 years away, visible to the naked eye on any clear winter night, burnished red at the shoulder of a hunter made of stars. Part 2. The first observers. The scientific story of Betelgeuse begins in the 1800s. But the human story of Betelgeuse is much older, long before telescopes, long before spectroscopy, long before we had a word for nuclear fusion, or even a concept of what stars were made of. Human observers around the world were watching Betelgeuse and noticing that it was strange. They did not have the language of modern physics to describe what they were seeing, but they recorded it faithfully in the medium they had: story, ritual, and oral tradition. Perhaps the most remarkable and most ancient of these records comes from the Aboriginal peoples of the Great Victoria Desert in Central Australia. Their astronomical traditions are among the oldest continuous bodies of scientific observation on Earth, stretching back tens of thousands of years. Unlike Western astronomy, which largely recorded stars as fixed points for navigation and calendar making, Aboriginal astronomical traditions often treated stars as living actors in ongoing narratives, and in doing so, preserved behavioral observations that would be invisible in any other format. In the traditions of these desert peoples, the constellation we call Orion was understood as a figure named Niaruna, a hunter pursuing the Ugarillia sisters, whom we know as the Pleiades star cluster. The story of Niaruna is a love story of cosmic scale, a pursuit that has been playing out across the sky for as long as anyone can remember. Niaruna is perpetually chasing the sisters across the heavens, and the sisters are perpetually fleeing. In the narrative, Niaruna uses fire magic to try to attack the sisters, drawing power into his right hand, the hand that on the sky map corresponds directly to the star Betelgeuse. What makes this story so scientifically significant is the detail that Niaruna's fire magic fluctuates. When Niaruna fills his hand with power, the star glows brightly, a threatening brilliant red. But the eldest of the Ugarillia sisters has fire magic of her own. She fights back, diminishing Niaruna's power, and as she does, his fire hand fades and dims. The story describes, with remarkable specificity, the behavior of a variable star. It encodes the observation that Betelgeuse periodically brightens and dims, that this cycle repeats, and that the star is notably red and notably unstable. This is not a myth that incidentally describes a star. It is a myth that is built around the observation of a star's behavior, a mechanism for preserving empirical astronomical data across generations without writing. The Aboriginal peoples of Australia were not the only ancient observers to notice that Betelgeuse was unusual. Moving forward in time and across continents, we encounter a different kind of record: written documents from the ancient Mediterranean and Chinese civilizations. These records are rarer and more fragmentary, but in some cases they preserve information of extraordinary scientific value. In the 1st century BC, the Chinese court astronomer Sima Qian compiled a comprehensive catalog of bright stars, recording their positions, their names, and their colors. For each star he noted the apparent hue, a subjective assessment, but one made by a trained and careful observer under pristine pre-industrial skies. When Sima described the star we call Betelgeuse, he recorded it as having a yellow or orange-yellow color. This detail is easy to overlook, but it becomes remarkable when you compare it to what came roughly 2 centuries later. In the 2nd century AD, the Greek astronomer Claudius Ptolemy wrote out his great systematologue of the stars, known today as the Almagest, a work that would remain the authoritative reference for Western astronomy for over 1,000 years. When Ptolemy described Betelgeuse, he used the Greek word hypokeiros, which translates roughly as distinctively ruddy or markedly reddish. He was not describing a yellowish star with reddish tones. He was describing a star that was notably, obviously, strikingly red enough that its color was its defining characteristic. The shift from Sima Qian's yellow description to Ptolemy's red description is not a matter of subjective interpretation or linguistic accident. It is a physical change, The color of a star is determined by its surface temperature. A yellow star has a higher surface temperature than a red star. As a star of this type evolves, as it expands outward, and its outer layers cool, its color shifts from yellow toward orange toward red. What these two astronomers, separated by two centuries and half a world apart, were observing, without knowing it, was the final stage of Betelgeuse settling into its current bloated configuration. The star was cooling and reddening in historical time. They watched it happen. They wrote it down. And we can read their notes today and understand exactly what they saw. This is one of the most haunting things about the story of Betelgeuse. The star has been changing on a timescale perceptible to human civilization. We did not just discover a static object. We have been watching a process unfold, recording it in myths and catalogs and star charts of many generations, without ever quite realizing that all these records were chapters in a single continuous story. Part 3. The scientific baseline, the systematic scientific tracking of Betelgeuse's variability, began properly in 1836, when the English astronomer Sir John Herschel made an observation that would prove historically important. Herschel was conducting a survey of bright stars in the southern sky and paying careful attention to comparative brightnesses. On multiple nights of observation, he noted that Betelgeuse appeared to be outshining Rigel, the blue-white star at Orion's foot, which is normally the brighter of the two by a comfortable margin. Rigel, formerly Beta Orionis, despite usually being brighter than Alpha Orionis, was being beaten by the variable red giant at the hunter's shoulder. Herschel's records established the first hard data point in what would become a long-running measurement campaign. He recognized that this was not an anomaly or an error. Betelgeuse was genuinely, verifiably changing in brightness on timescales of months to years. Not centuries, not decades, months. The star was not just slowly evolving over geological time. It was actively pulsing. It was breathing on a timescale that human observers could track within a single lifetime. By the late 19th and early 20th centuries, professional astronomy had developed the tools to monitor this variability systematically. Organizations like the American Association of Variable Star Observers began coordinating networks of amateur and professional astronomers to track the brightness of Betelgeuse continuously over long periods. The data accumulated, points were plotted on graphs, patterns began to emerge from the noise. By the mid-20th century, astronomers had gathered enough data to construct a detailed light curve, a graph of the star's brightness over time, spanning several decades. When they looked at this curve, they saw immediately that it was not simple. It was not the clean, regular sine wave of a textbook variable star. It was messy, irregular, multi-periodic. It looked less like a heartbeat than like a noisy mix of several heartbeats, all beating at different rates and different volumes, their rhythms superimposed and interfering with each other. The mathematical tools to disentangle this complexity existed. Fourier analysis, a technique that decomposes any complex signal into its constituent frequencies, could, in principle, separate the overlapping cycles. When astronomers applied this technique to the Betelgeuse light curve, they found something they had not fully expected. The complexity did not resolve into a single clean frequency with noise around it. It resolved into two distinct, strong, persistent periodicities. The first periodicity was the one they had anticipated. At roughly 400 days, just over a year, Betelgeuse has a primary pulsation cycle. This is the star's main heartbeat, and the physics behind it are well understood. Stars of Betelgeuse's type pulsate through a mechanism involving layers of partially ionized helium in their outer envelopes. These layers become opaque to radiation when they are compressed and heated, trapping energy inside the star like a pressure vessel. The trapped energy causes the star to expand outward. As it expands, the temperature and pressure in the helium layer drop, and the layer becomes transparent again, allowing the trapped energy to escape. The star then falls back under its own gravity, compresses, heats up again, and the cycle repeats. This is called the kappa mechanism, named for the Greek letter used for opacity in Stezek's equations, and it operates in many different classes of variable star. It is the standard engine of stellar pulsation. For Betelgeuse, this 400-day cycle represents the outer layers of the star heaving in and out like the chest of a sleeping giant, driven by this opacity engine in the layers beneath. If the 400-day cycle had been the only signal in the data, the story of Betelgeuse would have ended there. Variable star, understood physics, case closed. But the second periodicity would not go away. At roughly 2,100 days, about 6 years, there was a second, stronger, longer rhythm in the data. Every 6 years, the star dimmed significantly and then brightened again. This long secondary period, or LSP, was not subtle. In some cycles, it contributed as much to the total brightness variation as the shorter primary cycle. And it had been there in the data the whole time, waiting for someone to look for it properly. The LSP presented astrophysicists with a serious problem, because it violated the fundamental relationship between stellar size and pulsation period. Part 4. The mystery of the long secondary period. To understand why the 2,100-day cycle was so troubling, you need to understand a core principle of stellar physics: the period-density relationship. The rate at which a star can pulsate, the speed at which its outer layers can move in and out, is determined by the star's density. Specifically, the fundamental pulsation period of a star is proportional to 1 over the square root of the mean density. In simpler terms, denser stars pulsate faster, and less dense stars pulsate more slowly. Betelgeuse is already an extreme outlier in terms of density. It is a supergiant, which means it has expanded to an enormous volume while its total mass has not increased. The outer layers of Betelgeuse are incredibly tenuous. The density of the star's outer atmosphere is lower than the best vacuum we can create in a laboratory. But even given this extraordinary low density, the numbers did not work. For Betelgeuse to have a fundamental pulsation period of 200 days driven by internal stellar mechanics, it would need to be so large and so diffuse that it would barely qualify as a gravitationally bound object. The star would essentially be dissolving into space. This was clearly not what was happening. Astronomers went through the standard checklist of alternative explanations. Could giant convection cells explain the long cycle? On Betelgeuse, convection operates on a scale that is simply alien to human intuition. Our Sun has convection cells, the granules visible on its surface, but they are small, thousands of kilometers across, and there are millions of them at any given time. On Betelgeuse, a single convection cell can span a distance larger than the orbit of Mars. These massive bubbles of hot plasma rise from the interior, bloom across the surface, and sink back down over months. When a cell rises, the surface is brighter. When it sinks, the surface is dimmer. Could the cycling of these giant cells explain the 6-year period? The answer is no, for a fundamental reason. Convection is inherently chaotic. It does not have a built-in clock. The timing of convective upwelling and downwelling is governed by turbulence, by the random mixing of plasma, by the chaotic interplay of temperature gradients and rotation. You can have statistical regularities in convective behavior, but you cannot have a strict, repeating, clockwork 200-day period from convection alone. It would be like expecting the boiling of a pot of water to produce waves that ripple at a perfectly regular frequency. It doesn't work that way. Could magnetic cycles explain the long period? Our own Sun has an 11-year magnetic activity cycle that influences its brightness and the number of sunspots visible on its surface. Could Betelgeuse have an analogous magnetic cycle that was producing the dimming? This idea is more plausible at first glance, but runs into a different problem. Red supergiants like Betelgeuse have very weak and disorganized magnetic fields compared to main sequence stars like the Sun. The physics of large, slowly rotating, highly convective stars tends to produce chaotic magnetic environments rather than the organized, cycling dipole fields that drive the solar activity cycle. The magnetic fields in Betelgeuse are not strong enough or organized enough to dim the entire star by the observed amount on a regular, repeating schedule. Both of these alternatives had been ruled out not just by theoretical arguments, but by observational data. Neither the convective cell model nor the magnetic cycle model could reproduce the observed light curve when plugged into computer simulations of the star. Both models produced variability that was either too chaotic or too weak or both. This left a single remaining class of explanation. If the dimming is not caused by anything happening inside the star, not by pulsation, not by convection, not by magnetic fields, then it must be caused by something external to the star. Something that moves around the star on a 6-year cycle, intercepting our line of sight at regular intervals and blocking some of the light. A strict, repeating cycle implies an orbit. An orbit implies a gravitating body. The star was not alone. The hypothesis that Betelgeuse harbored a companion star had been circulating informally in the astronomical community for years before the evidence became strong enough to take it seriously. The idea was attractive, but it faced a seemingly insurmountable observational obstacle. If there was a companion star, why couldn't we see it? Part 5. The invisible companion. The answer to that question is simply that Betelgeuse is too bright. The star emits approximately 1,000 times more energy than our Sun. It is one of the most luminous objects in the entire galaxy that is visible to the naked eye. Against that flood of light, a companion star, with the mass of our Sun, itself a fairly typical star, would be completely invisible in direct imaging. It would be like trying to spot a candle flame next to a bonfire, except the bonfire is 100,000 times brighter than any bonfire that has ever burned on Earth. Direct detection was out of the question with current technology. Astronomers needed indirect methods, ways of inferring the presence of the companion, not by seeing it directly, but by seeing the evidence it left behind in the behavior of the system. The first approach they tried was careful analysis of the radial velocity of Betelgeuse, the speed at which the star is moving toward or away from us along our line of sight. If a companion star is orbiting Betelgeuse, both stars orbit their common center of mass. This means that over the course of each orbit, Betelgeuse should move slightly toward and then slightly away from us. And this motion should produce a periodic Doppler shift in its spectrum. The light from Betelgeuse should be slightly blue shifted when the star is moving toward us and slightly red shifted when it is moving away, with the cycle repeating every 2,100 days. The problem is that Betelgeuse has enormously complex spectrum, full of turbulence and acoustic waves and convective motions and pulsations that each contribute their own Doppler signals. Disentangling the small, regular 6-year signal from this chaotic background was extraordinarily difficult, but the data accumulated over decades and analyzed with increasingly sophisticated statistical tools showed a persistent, low-amplitude radial velocity variation with a period consistent with the long secondary period. This was suggestive, but not conclusive. The signal was real, but it was marginal. The second approach was interferometry. This technique combines the light from two or more widely separated telescopes to create an interference pattern that carries information about the angular structure of the source, essentially creating a virtual telescope with the resolving power of a mirror as large as the separation between the actual mirrors. The Very Large Telescope Interferometer in Chile and similar facilities allowed astronomers to image Betelgeuse at angular resolutions far higher than any single telescope could achieve, resolving details on the stellar disk that would otherwise be completely blurred together. What the interferometric images showed was unexpected and revealing. The surface of Betelgeuse is not uniform. It is mottled and asymmetric, covered with bright and dark patches that reflect the underlying convective structure. This was not surprising. What was surprising was the large-scale asymmetry in the outer atmosphere, the extended envelope of gas that surrounds the stellar disk. This envelope was not centered on the star. It was systematically offset, elongated in one direction, and showed signs of being stirred by something moving through it. The third and most conclusive approach was spectroscopic mapping, using the detailed structure of the star's spectrum to track not just the bulk motion of the star, but the local motions of gas at different positions across the stellar disk and in the extended atmosphere. This technique, applied over nearly a decade of observations by a team by Andrea Dupree at the Harvard-Smithsonian Center for Astrophysics, provided the breakthrough evidence. When Dupree and her collaborators mapped the gas motions in Betelgeuse's atmosphere over the full duration of several SEER cycles, they found a pattern that could not be explained by any single star model. The gas on one side of the star was consistently moving in one direction, while the gas on the other side was consistently moving in the other direction. Not randomly, consistently, on the 6-year cycle, in a pattern that repeated faithfully with each revolution. This is called a dipole pattern. It is the signature of gas being dragged through space by a gravitating object. If a companion star is embedded in the outer atmosphere of Betelgeuse and orbiting its core, it will act like a spoon being dragged through thick batter. It will push gas forward in its direction of travel, pile it up in a bow shock in front of itself, and leave a turbulent wake of disturbed, compressed gas behind it. Gas on the side of the orbit where the companion is moving toward us will be blue shifted. Gas on the side where it is moving away will be red shifted. The result is exactly the dipole pattern in the atmospheric gas motions that the observations revealed. The team tracked this pattern through nearly 8 years of spectroscopic data. It appeared on schedule. It repeated. It was consistent with a companion object of roughly solar mass at a distance of several astronomical units from the core of Betelgeuse, embedded in the outer envelope, dragging the atmosphere around with it on its 6-year circuit. This was no longer a hypothesis. This was evidence. Part 6. The Great Dimming. A false alarm with a silver lining. Before we continue with the story of the companion and what its discovery means for the fate of Betelgeuse, we need to address an event that intersected with this scientific story in complicated ways. In late 2019, Betelgeuse began to dim. Not in the subtle, gradual way it had dimmed in previous 6-year cycles. It dimmed dramatically, publicly, and in a way that was impossible for casual sky watchers to ignore. From roughly October 2019 through February 2020, Betelgeuse to about 30–36% of its normal visual brightness. This made it roughly as bright as Bellatrix, the star at Orion's other shoulder, which is normally much dimmer than Betelgeuse. For the first time in the living memory of anyone watching the sky, the constellation of Orion looked visibly wrong. One of its defining features, one of the 10 brightest stars in the entire sky, had essentially dimmed out. The hull looked lopsided. The shoulder was gone. The timing was, from a public communication standpoint, unfortunate. Betelgeuse was already known to be a supernova candidate. Astronomers had been saying for years that the star would explode sometime in the next 100,000 years. Sometime in the next 100,000 years is not a very precise prediction, but it is precise enough to lodge in the public imagination, and the public imagination had been primed. When the star visibly dimmed, the immediate interpretation from many corners of the internet, and from some corners of the scientific press, was that the star was about to explode. Articles were written, video made, social media erupted. The hashtag Betelgeuse went globally viral. Serious news organizations ran breathless pieces asking whether the night sky was out to gain a second moon. The professional astronomical community was considerably more cautious. The dimming was real and remarkable, but supernovae do not typically announce themselves with a preliminary dimming visible over months. They tend to explode relatively quickly once the core collapse begins. Nevertheless, given the genuine uncertainty about Betelgeuse's internal state, observing time was requested, granted, and used in enormous quantities. The Hubble's telescope was pointed at Betelgeuse repeatedly. Ground-based observatories worldwide tracked the star in every available wavelength. More data was collected on Betelgeuse in the 12 months of the Great Dimming than in the entire previous 2 decades of careful monitoring. The explanation, when it came, was simultaneously anticlimactic and fascinating. Betelgeuse had not been preparing to explode. It had sneezed. More precisely, the star had experienced what astronomers call a surface mass ejection, analogous to, but far more violent, the coronal mass ejections that our own sun produces regularly. A massive convective cell on the surface of Betelgeuse had erupted, throwing an enormous blob of hot plasma, a mass roughly equivalent to several times the mass of our moon, into space at high velocity. As this plasma traveled outward from the star and moved into the cooler regions of the extended atmosphere, it cooled rapidly. Gas that cools rapidly in space does not remain gas. It condenses. Specifically, it condenses into tiny solid particles of silicate dust, the same basic material that makes up sand on Earth. The result was a massive cloud of dark dust that formed in the line of sight between Betelgeuse's photosphere and our telescopes. This cloud was not in front of the star in the sense of being between us and the star in space. It was very close to the star's surface, formed from material that had just left the surface. But from our perspective, it was blocking a substantial fraction of the light that would otherwise have reached us. The star had not dimmed. The star had hidden behind a curtain of its own exhaled matter. Eventually, as the dust cloud expanded and dispersed, the curtain lifted. By April 2020, Betelgeuse was brightening again. By summer, it had returned to approximately normal brightness. The great dimming was over. The supernova had not happened. The alarm was false. But here is the silver lining, and it is a genuinely important one. Because of the worldwide panic, or excitement, depending on your perspective, about the potential supernova, every major observatory on Earth had been dedicating significant resources to Betelgeuse for over a year. The dataset collected during and after the Great Dimming was unprecedented in its depth, resolution, and duration. Ultraviolet observations from Hubble, infrared observations from ground-based adaptive optics systems, radio interferometry from the Atacama Large Millimeter Array, high-resolution spectroscopy from Michel spectrographs at numerous facilities, all of it capturing the detailed behavior of Betelgeuse's atmosphere before, during, and after the dust event. This was the raw material that would allow Dupree's team and others to finally make the case for the companion star. The Great Dimming was a distraction. It was a red herring about the death of the star. But the data it generated was the key to solving the actual mystery. It is also worth noting that the Great Dimming and the 6-year cycle overlapped, which is one of the reasons the situation was so confusing. The 2019 to 2000 dimming happened during the minimum of the long secondary period, the point in the 6-year cycle when the companion's disturbed wake was most directly interposed between us and the stellar disk. The dust event and the companion-induced dimming occurred simultaneously, producing a dimming that was substantially deeper than either cause would have produced alone. This double dip confused the models and initially made it harder to separate the two phenomena. Once the dust cleared and astronomers could look at the residual dimming attributable to the 6-year cycle, the signature of the companion was cleaner and more evident than it had ever been before. Part 7. Inside the envelope, let us now talk about what it means, physically, to have a star orbiting inside another star's atmosphere. This is not a situation that appears in standard stellar evolution textbooks. It is a brief, transitional phase. In stellar terms, a blink that is extraordinarily difficult to observe because it requires being in the right place at the right time. We happen to be in the right place at the right time. The atmosphere of Betelgeuse is not a sharp boundary. There is no clear line where the star ends and space begins. Instead, the density of the gas decreases gradually and continuously as you move outward from the core, falling from the crushing pressures of the nuclear burning interior through the convective envelope, through the photosphere, where the visible light escapes, thromosphere, and a tinted outer envelope, a region sometimes called the Mall sphere because it is cool enough for simple molecules to form. And finally into the wind, the continuous outflow of gas that Betelgeuse sheds into space at the rate of 1 solar mass every 10,000 years. Siwara orbits somewhere in the outer regions of this structure. The gas it moves through is extraordinarily thin. The density is orders of magnitude lower than the density of Earth's atmosphere at sea level, lower even than the upper reaches of the mesosphere. In terms of the number of particles per cubic centimeter, the outer envelope of Betelgeuse is closer to a very good laboratory vacuum than it is to anything we normally think of as a gas. But it is not a perfect vacuum. And in the context of orbital mechanics, even an imperfect vacuum makes an enormous difference. This is because the effect of dynamical friction on an orbiting body does not depend on the absolute density of the medium. It depends on the ratio of the gravitational influence of the orbiting body to the density of the medium. Siwara is a massive object, comparable to our entire Sun, and it is moving at high speed through the outer envelope. Even though the gas it encounters with each revolution is extremely thin, the sheer volume of gas it encounters over the long arc of its orbit accumulates. The drag is not enormous by the standards of a body moving through water, but it is not zero, and because it acts continuously, over thousands of orbits, over millions of years, even a tiny drag adds up to a fatal loss of orbital energy. The physics of this process were worked out in detail by the Indian-American astrophysicist Subrahmanyan Chandrasekhar in 1943, in work that now goes by the name Chandrasekhar dynamical friction. Chandrasekhar showed that when a massive object moves through a field of lighter particles, the gravitational interaction between the massive object and the surrounding particles creates an overdense wake directly behind the moving object. The particles it has passed by are gravitationally attracted toward it, fall slightly behind it, and accumulate into a region of elevated density in the object's trail. This overdense wake then exerts a backward gravitational on the object. The object is, in a sense, being pulled backward by the gravity of its own wake. This is fundamentally different from ordinary fluid friction, where the resistance depends on the viscosity of the medium. Dynamical friction is gravitational in origin and operates even in media that are so thin they would be considered vacuums for ordinary purposes. For Siwara, this means that with every orbit around the core of Betelgeuse, the star loses some of its kinetic energy to the surrounding gas. This energy does not disappear, it is deposited into the gas in the form of heat and turbulence, stirring up the outer envelope of Betelgeuse and adding energy to the extended atmosphere. But for Siwara, the loss of kinetic energy has a direct and serious consequence. The star's orbit becomes a spiral. This is the counterintuitive reality of orbital mechanics in a resistive medium. When you lose orbital energy, you do not slow down and stay in your current orbit. You fall inward. You drop to a lower orbit where gravity is stronger, and in that lower orbit you actually move faster than you did before. The orbit shrinks and the orbital speed increases, but the total energy, kinetic plus potential, decreases. The orbit is decaying. Siwara is moving faster now than it did a million years ago, but it is also lower in the gravitational well, and the gas around it is denser, and the drag is stronger. The spiral is accelerating. Part 8. The feedback loop, the decay of Siwara's orbit, is not a simple linear process. It is a runaway feedback loop, and understanding its dynamics requires following the cascade of consequences from one effect to the next. Siwara loses energy to dynamical friction. Its orbit decays. It moves to a lower, tighter orbit. Step 2. At a lower orbit, the gas density is higher. The outer envelope of Betelgeuse is denser near its core than in its outermost reaches, not dramatically so, because the structure of the envelope is relatively uniform, but measurably so. Higher gas density means more particles per unit volume that Siwara must gravitationally interact with on each orbit. The dynamical friction force increases. The rate of orbital energy loss accelerates. Step 3. The orbital energy lost to friction is deposited into the gas. This is heat. This is turbulence. This energy injection into the outer envelope has a direct effect on Betelgeuse itself. The star's envelope is held in a delicate balance between gravity pulling ward and gas pressure plus radiation pressure pushing outward. Adding energy to the envelope tips this balance. The envelope heats up slightly. It expands. The outer layers of Betelgeuse puff outward, increasing the star's apparent size. Step 4. As the outer layers expand, they reach lower gas densities for any given orbital radius of Siwara. But they also expand the total volume of gas through which Siwara must move. The net effect on the friction depends on the geometry, but the key point is that the expansion of the envelope means that Siwara is now snabber inside the star relative to its outer boundary. The star has grown around it. Step 5. The faster Siwara orbits, the more angular momentum it deposits into the envelope. This spins up the outer layers of Betelgeuse. Outer envelope of the star begins to rotate faster than it would if Betelgeuse were a single star evolving in isolation. This last point is one of the most important observational signatures of the ongoing merger process. It is also one of the clearest pieces of evidence that something very unusual is happening with Betelgeuse. When a massive star like Betelgeuse evolves off the main sequence and expands into a red supergiant, conservation of angular momentum dictates that it should slow its rotation dramatically. A figure skater extending her arms slows down. A collapsing gas cloud spinning up its star slows down when that star bloats outward. The expansion should reduce the surface rotation speed to a tiny fraction of the main sequence value. Based on Betelgeuse's current size, astronomers estimated, before the companion was discovered, that its surface should be rotating at somewhere between 0.5 and 1 kilometer per second. This is an incredibly slow crawl for a star. By comparison, our sun rotates at about 2 kilometers per second at its equator. A star as large as Betelgeuse, rotating at solar speeds, would be spinning so slowly relative to its size that one rotate would take over a century in human time. The measured rotation speed of Betelgeuse's surface is approximately 15 kilometers per second. This is 15 times faster than simple evolution would predict. For decades, this anomalously high rotation rate was considered a puzzle, a number that sat in the data without a good explanation. Some astronomers suggested that Betelgeuse might have accreted material from a companion at some point in the past. Others suggested that the measurement itself might be contaminated by large-scale convective motions mimicking rotational velocity. Neither explanation was fully satisfying. The discovery of Siwara explains the fast rotation cleanly and completely. The companion star is in an orbit, and orbital motion carries angular momentum. As friction bleeds orbital energy from Siwara into the envelope of Betelgeuse, it also transfers angular momentum. The envelope of Betelgeuse is being spun up by the angular momentum deposited by the in-spiraling companion. The fast rotation is not an anomaly. It is a direct measurement of the ongoing merger. It is the star telling us, in the language of spin, that something is orbiting inside it. Part 9. The future of the system. Let us now talk about timescales. From a human perspective, the process we are watching appears almost perfectly static. The orbital period of Siwara is 6 years. The orbital decay per cycle is small. The companion drops by a tiny fraction of its orbital radius with each revolution. On any human timescale, the situation looks stable. The star will be there tonight as it was last night, and it will be there next year as it is this year, and it will be there in 100 years as it is today, with no detectable change to the naked eye. We are not watching a fast event. We are watching an epoch in the history of a stellar system, a phase that, from the perspective of a human civilization that measures time in decades, appears frozen. But from the perspective of a star, an epoch can be very brief. Computer models of common envelope evolution, the technical term for the phase a binary system enters when one star engulfs the other, suggest that once the companion is embedded in the envelope, the time scale for its eventual inspiral to the core is set by the density structure of the envelope and the mass of the companion. For Betelgeuse and Siwara, given the current estimates of the envelope density profile and the companion's orbital parameters, the inspiral is complete on a timescale of roughly 1,000 to 20,000 years. To a geologist, 10,000 years is nothing. It is the span of recorded human civilization. To a stellar astronomer, it is essentially instantaneous. Betelgeuse has been a star for about 8 million years. Its time as a red supergiant has lasted hundreds of thousands of years. If you compress the entire lifetime of Betelgeuse into a single human year, the remaining inspiral time would be about 40 minutes. We are final scene. What happens when Siwara finally reaches the core? The core of Betelgeuse is a very different environment from the outer envelope. It is not a diffuse, cool gas. It is an ultra-dense, ultra-hot nuclear furnace. At the current stage of Betelgeuse's evolution, the core is almost certainly burning carbon or neon, the products of earlier stages of nuclear fusion that fused hydrogen to helium, helium to carbon, and carbon to more complex elements. The core is surrounded by shells of fusion at different stages, like an onion, each shell processing the ash of the shell above it. This structure is gravitationally stable as long as the energy output of the fusion reactions is sufficient to support the weight of the overlying layers. The core walks a knife edge between collapse and explosion. When Siwara, a solar mass star, plunges into this structure, the result will be catastrophic. The companion carries an enormous amount of gravitational potential energy, which was acquired over the entire history of its inspiral. This energy, released in a short time, will be deposited into the deep interior of Betelgeuse. The shock waves generated by the collision will propagate outward through the star at close to the speed of sound in the stellar medium. Fast by any ordinary standard, but slow enough that the energy has time to build up and interact with the fusion shells before escaping. Before the final plunge, though, there will be a visible precursor. As Siwara spirals into the denser inner regions of the envelope, the energy it deposits will increase dramatically. The outer layers of Betelgeuse will be heated from within more intensely than at any previous time in the merger. Material will be driven off the surface at high rates. The mass loss, already elevated compared to a normal star, will spike further. Betelgeuse may shed a substantial fraction of its remaining envelope mass in a relatively short time, thousands of years, creating an expanding shell of gas around the system that could one day become the nebula in which the supernova remnant is embedded. The actual merger event, the moment Siwara's core reaches the core of Betelgeuse, will produce an enormous burst of energy. This is sometimes called a merger novae or red nova, a luminous transient event that is not quite a supernova, but is far brighter than any ordinary stellar outburst. The gravitational energy released when a solar mass object falls to the center of a star the size of Betelgeuse is enormous. It could temporarily increase the luminosity of Betelgeuse by many orders of magnitude. Some estimates suggest it could briefly become as bright as a crescent moon, as seen from Earth, visible in daylight. This will not be the end of the story. After the merger, what remains will be a single, more massive, rapidly rotating star, a hybrid object that carries within it the nuclear history of both progenitors. Whether this merged object will immediately detonate as a supernova, or whether it will stabilize into a new configuration and survive for some additional time, is one of the most debated questions in current stellar evolution research. Part 10. 2 o'clocks. There are 2 clocks running simultaneously in the story of Betelgeuse, and both are counting down. The first clock is the nuclear clock. Betelgeuse is running out of fuel. The star has burned through its hydrogen, it has burned through much of its helium. It is now burning carbon and neon in its core, and moving progressively through heavier elements toward iron. Each successive fuel burns faster than the last. The time from the end of neon burning to the end of silicon burning, and from there to the accumulation of iron in the core, and the inevitable core collapse, is measured not in millions of years or even thousands of years, but in decades and years, at the very end, days and seconds. The silicon burning phase, the last stage before iron takes over and fusion can no longer generate energy, lasts about a day. After that, the iron core grows until it exceeds the Chandrasekhar limit and collapses. This triggers the supernova. The timeline of the nuclear clock is uncertain. We do not know exactly how much fuel remains in the core. Estimates range from essentially immediately, the star could detonate any time within the next 1,000 years, to as much as 100,000 years in the future. The uncertainty is genuine, because we cannot directly observe the core of Betelgeuse. We can measure the surface. We can measure the atmosphere. We can model the interior with computer simulations. But the deep interior is hidden from us by the enormous optical depth of the outer layers, and small uncertainties in the model inputs translate into large uncertainties in the predicted remaining lifetime. The second clock is the orbital clock. We can now estimate this one considerably better than the nuclear clock, because we can observe the companion directly, in the sense that we can observe the wake it leaves. We know the orbital period. We can estimate the orbital radius. We have models of the envelope density structure that allow us to calculate the dynamical friction force. These calculations suggest that the orbital decay will complete. Siwara will reach the core on a timescale of roughly 10,000 to 20,000 years. The question of which clock runs out first is genuinely open. If the nuclear clock expires before the orbital clock, if Betelgeuse reaches core collapse before Siwara reaches the center, then we will see a conventional core collapse supernova, type 2, with the interesting complication of having an companion that was actively modifying the pre-supernova structure of the star. This complication is not trivial. The presence of a companion in the envelope changes the density and temperature structure of the star, and that will affect the properties of the supernova, the shock propagation, the nucleosynthesis, the light curve, the properties of the remnant. If the orbital clock expires first, if Siwara reaches the core while Betelgeuse has not yet collapsed, then the merger event itself may trigger the supernova. The energy deposited by the collision could destabilize the precarious balance of the fusion shells and trigger the core collapse prematurely. In this scenario, the merger and the supernova happen together, and what we see from Earth is a combined event, a merger nova immediately followed by or coincident with a core collapse supernova. This would be spectacularly bright. It would be the most visible supernova in the Milky Way in over 400 years. It would be visible in daylight for weeks. The aftermath of either scenario is a neutron star or possibly a black hole, surrounded by an expanding shell of hot gas that will glow for thousands of years as a supernova remnant. Similar to the Crab Nebula, the remnant of a supernova observed by Chinese and Japanese astronomers in 1054 AD, which is still visible in Taurus with a small telescope. The Orion Nebula of the future will have a new opponent, a hot, glowing gas cloud at the location of what is currently the star Betelgeuse. Part 11. The laboratory in the sky beyond the drama of the specific outcome. The discovery of the companion in Betelgeuse has profound implications for how we understand the evolution of massive stars in general. For decades, stellar evolution theory was built predominantly on single star models. You start with a gas cloud of a certain mass. It collapses. It ignites, burns through its fuel. It evolves off the main sequence, becomes a giant, burns heavier elements, and eventually explodes or collapses. This sequence was understood in considerable detail, and it matched observations of stellar populations and supernova remnants reasonably well. Single-star evolution was good enough for most purposes. But as observational capabilities improved, a disturbing pattern emerged. The supernovae we were actually detecting in other galaxies did not always match the predictions of single-star evolution models. Many supernovae showed spectroscopic signatures of material in the surrounding space that could not have been shed by a single star evolving in isolation. There were supernovae with unusual light curves that seemed to require pre-existing circumstellar material arranged in specific geometries. There were post-explosional remnants that showed asymmetries inconsistent with a spherical explosion from a single-point source. The answer to many of these discrepancies is almost certainly binarity. Most massive stars are not single. They are in binary or multiple systems. Observations of massive star populations suggest that the majority of stars with masses above 10 solar masses, the minimum mass for a core collapse supernova, are in close binary systems. Many of these systems will interact before the primary star explodes. One star will swell into a giant, overflow its gravitational boundary, and dump mass onto its companion. Or both stars will merge, or the primary will explode, and the companion will be ejected at high velocity. Binary interactions are not a minor perturbation to the standard picture. They are a fundamental part of the picture. Betelgeuse gives us a case study in one of the most extreme forms of binary interaction, common envelope evolution. This phase is theoretically well understood in outline, but observationally extremely challenging to study, because it is brief. In the full lifetime of a star, the common envelope phase lasts only a few thousand years at most. In a galaxy full of billions of stars, the odds that any particular system is in the common envelope phase at any given time are very low. Finding one close enough to study in detail is extraordinarily rare. We appear to have found one. And we have found it in a star that has been continuously observed for nearly 2 centuries, giving us a baseline against which to measure the changes induced by the companion. This is an irreplaceable scientific opportunity. The data being gathered on Betelgeuse right now, the spectroscopic maps of the atmospheric gas motions, the ultraviolet monitoring of the chromosphere, the infrared imaging of the dust-forming outer layers, the radio measurements of the circumstellar wind, are building a case study of envelope evolution that will inform stellar evolution models for generations. The next planned major observational campaign is timed for around 2027, when the companion is expected to emerge from behind the stellar disk, as seen from our line of sight, potentially allowing the most direct detection yet of Siwara's influence on the system. There is also the broader question of what systems like Betelgeuse tell us about the formation of compact object mergers, the collisions between neutron stars and black holes that produce gravitational wave events detected by LIGO and Virgo. These mergers happen because binary systems with close orbits decay over time, but the pathway from a wide binary to a tight neutron star binary runs through a common envelope phase. Understanding common envelope evolution is essential for predicting the merger rates of compact objects, which in turn is essential for understanding the gravitational wave universe and the synthesis of heavy elements in neutron star mergers. Betelgeuse is not just a colorful dying star with an unusual companion. It is a key to understanding a chain of physical processes that extends all the way to the origin of gold and platinum in the universe. Part 12. What the ancient observers knew. Let us step back, for a moment, from the physics and reflect on the human dimension of this story. For thousands of years, people looked at Betelgeuse without knowing what it was. They did not know it was a ball of plasma held together by gravity, fusing atomic nuclei in its core, illuminating a bubble of space 700 light-years across. They did not know it was a dying star in the last fraction of a percent of its life. They did not know it was a binary system with an embedded companion spiraling toward a catastrophic end. They had none of this language, none of these concepts, none of these instruments, and yet they watched it. They watched it closely enough to notice that it changed. They embedded those changes into stories that survived for thousands of years. The Aboriginal astronomers of Australia created a narrative about fire magic and pursuit that encoded a quantitative observation. The star pulsates, it brightens and dims, the cycle repeats, in a format that transmitted reliably across dozens of generations. The Chinese court astronomer Sima Qian noted a color that no longer matches, preserving evidence of the star's evolution. Ptolemy wrote down its redness with a specific Greek adjective that distinguished it from other nominally red stars, and that word survives in manuscripts copied and recopied across 2 millennia. This is what human observation looks like at its best, not the observation aided by billion-dollar instruments, though that too has its place. The observation driven simply by attention, by the sustained willingness to look at the same thing over and over across seasons and years and lifetimes, to notice what changes, to preserve what you notice in whatever medium is available to you, so that people who come after you can add their own observations to yours and eventually build a picture that no single lifetime could contain. The story of Betelgeuse is, among other things, a story about the cumulative power of human attention. The discovery of Siwara did not happen because of any single observation or any single instrument or any single genius. It happened because hundreds of people over nearly 2 centuries, and perhaps thousands of people over millennia, if we include the Aboriginal astronomers, kept looking, kept recording, and kept adding their data to the growing pile. The 6-year cycle was hidden in that pile for decades, waiting for someone with the right mathematical tools to find it. The companion was hiding in the data for years, waiting for an accumulation of evidence precise enough to make the case compellingly. This is also a story about the power of indirect detection. We have not seen Siwara. We cannot currently take a photograph of it. It is hidden behind a wall of stellar light 100,000 times brighter than itself. But we have seen its footprint in the gas. We have seen the dipole pattern in the atmospheric motions that its gravitational drag produces. We have seen the anomalously fast rotation that its angular momentum transfer causes. We have seen the long secondary period that its obstructing wake creates in the light curve. From these indirect signatures, scattered across multiple wavelengths and multiple observational technique accumulated over many years, we have built a picture of an object we cannot directly see. This is how much of modern astrophysics works. The universe is mostly opaque to our most intuitive sense, vision. We cannot see the cores of stars. We cannot see the inside of black holes. We cannot directly observe the dark matter that constitutes most of the mass in the universe. We cannot watch the nuclear reactions that power the stars. We infer all of these things from the signals they leave in observable quantities: brightness, spectrum, timing, proper motion, gravitational effects on visible neighbors. We read the universe the way a detective reads a crime scene, assembling evidence that points toward a reality that was never directly observed. The detective metaphor is apt for Betelgeuse. The crime scene is the star's behavior, the strange double periodicity, the fast rotation, the asymmetric atmosphere, the disturbed outer envelope. The detective is the community of astronomers who looked at those clues and followed them, one by one, decade by decade, instrument by instrument, until the picture became clear. And the culprit, the hidden actor behind all the anomalies, turned out to be a companion star orbiting inside it, fighting the drag, carving a wake through the gas, spiraling toward an end that is as inevitable as any ending in physics. Part 13. Looking uppy. The next time you find yourself outside on a clear winter evening, look south and find Orion. It is one of the most recognizable constellations in the sky. The three belt stars in a diagonal line, the two bright stars at the shoulders above and the two bright stars at the feet below, the faint smudge of the Orion Nebula hanging from the belt like a jewel. It is the constellation of the hunter, and it has been called that, or something very like that, in cultures from Australia to Arabia to ancient Greece. Find the left shoulder from our perspective, the upper right star as you look at the figure. It is the red one, not the blue-white of Rigel at the foot, not the cold blue of Bellatrix at the other shoulder, the warm, rust-reddish point of light that marks where the hunter holds his club or draws his bow, depending on how you tell the story. That is Betelgeuse, Alpha Orionis, the shoulder of the giant, Nearuna's fire hand, the star that has been changing before human eyes for longer than writing exists. What you are looking at is a sphere of plasma roughly 1 billion kilometers across, burning at temperatures that would vaporize any matter we have ever touched, producing enough light that if you replaced our sun with it, you could read in its glow from the distance of Saturn. The light reaching your eyes right now left that star approximately 700 years ago, around the time that Dante was writing the Commedia and the Black Death was sweeping through Europe. The star you are looking at is the star as it was in the early 14th century. The star as it is right now, tonight, in real time, you will not be able to see for another 7 centuries. Inside that ancient light, if you could see at the right wavelength with the right instrument with the right sensitivity, you would see the swirling pattern of gas being dragged around the stellar disk by a companion you cannot directly observe. You would see one side of the atmosphere blue shifted and the other red shifted, the dipole signature of an orbital motion happening inside the star. You would see the elevated rotation speed of the outer envelope, spinning faster than physics says it should, driven by the angular momentum deposited by a solar mass object fighting the gas on its long inward spiral. You would see 2 clocks counting down. The nuclear clock in the core, ticking toward the moment when the iron ash becomes too heavy for the fusion reactions to support, and the star collapses in less than a second, rebounding in a shock wave that tears the star apart and briefly outsheens the entire galaxy. And the orbital clock ticking toward the moment when the companion finally loses its last erg of orbital energy and falls through the dense inner layers into the core, triggering an explosion of gravitational energy that will announce itself to the entire local group of galaxies. You would see a laboratory for stellar physics that we will not have another chance to see in this detail for a very long time. You would see evidence for a binary interaction that changes how we understand the life cycles of massive stars, the formation pathways of neutron-star mergers, the production of heavy elements. You would see the result of thousands of years of human observation, the careful watching and recording of a tiny red dot in the sky, by people from cultures separated by oceans and millennia, who nonetheless noticed the same thing. This star is different. This star moves. This star is alive in a way the other stars are not. And you would see something that is, when you hold all of it together, simply beautiful. Not beautiful in a sentimental or metaphorical sense, but beautiful in the deep sense of a system whose behavior, at every scale and in every detail, reflects the underlying physical laws with perfect fidelity. The friction follows from Chandrasekhar's equations. The spiral follows from Newton's laws. The pulsation follows from the opacity of helium ions. The color follows from the temperature, which follows from the luminosity, which follows from the mass, which was determined before the star began. Every aspect of what we see when we look at Betelgeuse follows from first principles that were laid down in the first moments of the universe, when the laws of physics crystallized and the initial conditions were set. We did not make this picture. We found it. That is the wonder of it. The star has been doing this, the pulsating, the spiraling, the churning of the atmosphere, the slow spin-up, whether or not anyone was watching. For most of the universe's history, no one was watching. There were no eyes, no instruments, no mathematics, no language for describing what was happening. The star was burning and spiraling and oscillating into the void alone for millions of years, sending its light in all directions and receiving no response. And then on one small rocky planet, orbiting a very ordinary yellow star, in the outer arm of an unremarkable spiral galaxy, creatures evolved who could look up and notice that one particular reddish dot in the sky was changing. Who could tell stories about it, write it in catalogs, build instruments to measure it, develop mathematics to analyze it, launch telescopes to study it in wavelengths invisible to the naked eye, and eventually assemble all of that information into understanding of is 700 light years away from the planet where those creatures happen to evolve. That, in the end, is what the Betelgeuse story is about. It is not just about one dying star with a companion it is slowly swallowing. It is about the capacity of a small, fragile, remarkably persistent species to point at the sky, and one observation at a time, understand what it sees, to find the signal in the noise, to follow the evidence where it leads, to revise the story when the evidence demands it, to discover, again and again, that the universe is stranger and richer and more interesting than the previous version of the story was able to contain. Go outside tonight. Look at Orion. Look at the red shoulder. Remember that there is a second star in there, a sun likes fighting the friction, churning the gas, spinning up the giant, spiraling toward its end. Remember that you are looking at light that left the star before Chaucer wrote the Canterbury Tales, before the Great Plague, before the Renaissance. Remember that Aboriginal astronomers were watching the same star and recording its variability in oral tradition long before any of those happened. And remember that in roughly 10,000 years, give or take, the companion will reach the center, and something extraordinary will happen. And if there are people around to see it, they will watch a star brighten in the shoulder of Orion until it is visible in the middle of the day. And if those people have built the instruments and the mathematics and the accumulated observational record to understand what they are seeing, they will recognize it. They will say, that is the merger. That is what happens when a star is swallowed. That is the Siwara event. We knew this was coming. We watched it happen, one orbit at a time, from the beginning. We are those people at the beginning. We are the ones who first figured it out. And that, for all the humbling scale of the universe pressing down, of a single species on a single planet, is no small thing. The 6-year signal was never a heartbeat, it was a footprint. And now we know whose.